Okay, hi. So this is problem number 1. And in this problem, we are building 44 homes each year. Okay. So that's every year, once a year. And we're beginning with 47,000 homes. So typically what we want to do is, if this is a problem with dates, we typically want that first date to be time 0. So I'm going to call this x, or t equals 0 for 2002. So let's just make a quick data list. At time 0, okay, which is really the year 2002, and time 0, they're giving me the population, right? The number of homes, so 47,000 homes. Okay, so this is the time, and this is the number of homes. Now, what about at time 1? So in 2003, which would, of course, be year 1, we're going to have 47,000 plus we're building 44 homes. Okay, so of course we can just add that together, 47,000 and 44 if we want, but I'm just going to leave it like this so you can see where things are coming from. In 2004, at time 2, we're going to have 47,000 plus 44, that's from last year, plus this year we're building a new 44 homes. Let's go one more year. Okay, in 2005, which is time equals 3, we've got my initial 47,000 plus 44 from the first year, 44 from the second year, and then the third year we're building a new 44 homes. So what's the pattern? The 47,000 is not changing, right? So the 47,000 is constant. In fact, that's a constant called the initial value, because it's what we start with. In fact, it's the value when the input is 0. When you plug a 0 in, the number you get is called the initial value. Okay? It's also called the y-intercept if you graph the relationship, if you graph the equation, the y-intercept, or the b term. Okay? Now, we're then adding the same number over and over again. Okay? So when we add the same number over and over again, we can kind of do that more efficiently by just multiplying. So I can call this 44 times 3. Okay? So I could write this particular population or number of homes as 47,000 plus 44 times 3. Okay, I could of course write this as the 47,000 plus 44 times 2. I could write this as 47,000 plus 44 times 1. And if I wanted to, I could even write this as 47,000 plus 44 times 0, because there's no 44s being added there. Okay, so what we see is this particular number right here, this number that I'm going to kind of circle in red, is changing every year, and that's telling us the number of copies of the 44 that get added. Okay, so this is the number of copies of the 44 that get added each time period. Okay, to reach the current value. Now, when we do that, we need a name for these quantities. So the 44, the quantity that we add over and over again, has a name. Okay, it's called the slope. Okay, or constant rate of change. So the quantity that we're adding over and over again is called the slope, or the constant rate of change. You'll see different descriptions of it. It's what we add over and over again. Okay, it's the quantity we add over and over again. Okay, and then the 3 or the 4 or whatever these numbers are over here that keep changing every time, we have a name for that also. Okay, these guys that I kind of circled in red. Okay, that's called the input value, because nothing else is changing. Notice the 47,000 is the same everywhere. Not changing, right? The 44, the identity, this number itself, 44, is not changing. What's changing is the number of times we're adding the 44, and we keep track of that with this multiplier. So the multiplier that multiplies your constant rate of change. So this is my constant rate of change, or slope. Okay, it's that 44 everywhere we see it. That's my constant rate of change. The number of times we add that is kept track of by this input value. The input value tells me how many times, how many copies, how many times we add the slope number, or constant rate of change number. Okay, and that's what's changing. What's changing is that input value. Okay, everything else is staying the same. The identity of the 44 is staying the same. the 47,000 staying the same every year. All that's changing is the number of 44s, which is kept track of by this T or X, whatever you want it, whatever label you want to give to it. Okay, so we're using T for time here. So it looks like what's going on is if I keep going, let me make a little bit of, well, I'll just kind of write it down here. If I keep going, let's say to year, let's say I go to year 2010. Can you predict what's going to happen in year 2010? Okay, that's going to be T equals 8, right? Because we're doing years since 2002. So I'm going to have what? 47,000 plus how many 44s? 44 times 8. We're going to have 8 copies of the 44. Okay. What do you think is going to happen in 2018? So they're asking me about 2018. In 2018, that's time equals what? 2018 is how many years after 2002? It's 16 years after 2002. So I'm going to have what? 47,000 plus 44 times 16. Okay? So we just keep working like that. Now, is there a general equation for all of this? They're not asking us for it, but what would the general property be? Every year, if you kind of notice, let's say I go to whatever year I'm at, I'm going to have 47,000. So we can call this the Y value is equal to 47,000 plus what? We're taking 44 every year times the number of years. And so what do I want to call the number of years? Since it's changing all the time, it's not a fixed amount, it's changing, the years is changing, we need to call it a variable. And we'll call it either X or T or some letter that indicates a change in quantity. I'll use T for time, you can use X if you like. So notice this is a Y equals MX plus B situation. I could write this as Y equals 44 times T plus 47,000 if I like. Notice this is called the slope, or the M. Okay, the time is like my X, because it's my input, and then this is plus the starting value, or B. 47,000 is the starting or y-intercept or B value. So it's kind of an MX plus B situation if you want to generate an equation for this. You don't have to solve the problem, you just have to spot the pattern. Okay? All right, so let's go on to problem 2. Okay, so for problem number 2 here, notice that they're giving us what's called a recursive rule. So if you remember from section 2.1, recursive rule means that each term depends on the previous term. So each value or each term depends on the previous one. Okay, the previous term. Now, in the language of sequences, each term, this would be called term Pn, the nth term. Okay, P being, I guess we're using P for the sales for some reason. Okay, so the nth sales level, Pn, depends on the previous term, which would P in time period n minus 1. So the subscript or index is telling you the time period in each case. So the n or the n minus 1, these are telling you the time period. Okay, so the nth time period depends on the n minus first time period. So that means that we need to be told the first one, because the first one would have to depend on the one before it, and there is nothing before the first one. So they have to tell us the initial, okay, and they're giving it to us right here. Okay, that's the initial. So when we have a recursive rule, we need at least the first value told to us, okay, which they're giving it. They're giving it to us. So let's go ahead and start writing out some values here. So in 2005, which we'll call n equals 0, year 0, okay, we've got that the value of this sales in year 0, which is really year 2005, is told to us to be 35. Now this is in thousands of dollars. So what they really mean is $35,000, okay? So I'll just kind of, well, we'll just remember that's 35,000. Now, what about in 2006? 2006 would be the first n equals 1 year, okay? And P1, we're told, is equal to what? P1 take away 1, because at this point, the n is my n is 1. If my n is 1, then I have to do Pn minus 1. So let's kind of just write this as Pn minus 1. But Pn minus 1, so it's going to be Pn minus 1 plus 15. But Pn minus 1 is really P0. Whoops, plus 15. Because the term before the first one is the 0. So n minus 1. If n is 1, then n minus 1 would be a 0. So in other words, this is saying that we take that each term depends on the prior term, the term before it, plus 15. So I'm going to take the price. So the first term depends on the prior term, P0, plus 15. Now, do I know what P0 is? And the answer is I do. It's 35. I just read it off my chart that I built. So 35 plus 15 is 50, right? And we just keep going. Okay, so in 2007, we're going to have n equals, that's my n equals 2 year. Okay, so P2 is going to be what? P2 minus 1, because we're reducing the index by 1. So 2 minus 1, sorry about that, plus 15, which is going to be P1 plus 15. And what is P1? P1 is the result that we got here, right? This is where we computed P1, and the result we got was 50. Okay, so I'm getting 50 plus 15, which is 65. Okay, and we're going to keep going until we reach 110. Okay, so if you keep going in this process with the numbers I have, you should see that you reach this in by n equals 5. Okay. All right. So I'll do one more with you. So at 2008, that's n equals 3. We have P3 is going to be, and I'm going to shorten this a little bit. It's going to be the previous value plus the 15. Okay. What's the previous value? 65 plus 15, which is 80. I'll just go ahead and finish this up for you. 2009, that's n equals 4. P4 is going to be what? The previous value, which is P3 plus 15. What is P3? P3 is 80. Plus 15 is 95. And let's go one more. So 2010, n equals 5. P5 is going to be the fourth value, because we always take the previous value, plus 15. So that's going to be the previous value of 95, plus 15 gives me my 110, which is what I'm looking for, because remember, even though they're saying 110,000, that means that, that the p-value has to be 110, because everything's measured in thousands. So think of it as $1,000 bills. So we want to know when we have 110 of these $1,000 bills. Think of this as measuring the number of $1,000 bills, these values. Right, which is how we measure everything anyway, right? $1,000 bills, right? Everyone measures things in $1,000 bills. Nah, well, you know. But anyway, so that's the number of $1,000 bills. So we're going to have 110 of them in year 5, which corresponds to 2010. Okay, so I would answer this as year 2010. Okay. So again, we're now, why is this not in the sequences section? Like, why is this not in the last section? Why is this in the linear modeling linear growth section? Because what's happening is we're increasing by the same amount all the time. In fact, if we wanted to write an equation for this, what would it look like? We're starting, my starting value, or the b, or also called the b in y equals mx plus b language, is equal to 35, right here. And then we increase by the same amount every time. If you're increasing by the same amount all the time, that same amount is called the slope, or the constant rate of change. And what's the amount we're increasing by every time? Well, let's see. We're adding 15, and each time period we're adding 15 to the previous time period. So notice these outputs are going up by 15 every year. Right? That's going up by 15, going up by 15, going up by 15, which makes sense because we keep adding 15, right? How many 15s get added? We add a 15 every year. Okay, so we're going up by all the time. We're going up by 15 each year. Okay, so we're going up by a total. So the total we're going up by is how much? 15 times the number of years. What do you want to call the number of years? We'll call it n if you like, for the number of years. Okay, so notice in year 0, we have 0 copies of 15. We haven't gone up by 15 at all. In year 1, we have 1 copy of 15, which makes sense. We have gone up by 1 copy of 15. By year 2, we've actually gone up by 2 copies of 15 because we had the 15 from the previous year and then this year. Okay, so etc. So this is working. The total is 15, which is how much we go up by each year, times the number of years. So the equation we would have here is that Pn, the value Pn, is going to equal the starting amount, 35, plus the change times the number of years we're doing that change. N is the number of years that we're doing the change. The change is 15. Okay? And so that's my equation. That's a y equals mx plus b scenario. Okay, this is like your m, this is your x, and this is your b. So it's like mx plus b. Okay? And so there we go. So it is linear. Okay, we're just kind of constructing it in the form of a sequence of values, but it's the sequence is resulting in adding the same amount all the time. If you always add the same amount all the time, it's a linear situation. Okay, linear means add the same amount. The same amount that you constantly add is called the slope. Okay? All right, that's called my slope or my constant rate of change. And the number of times you add that is your input, or x value, or n value. That tells you how many copies of the slope you keep adding over and over again. Okay? And there we go. All right, so let's go on to problem 3. Okay, so here we are in problem 3. In problem 3, again, they're giving us a they're describing a process as a sequence, and it's a recursive sequence. Each term in the sequence depends on the prior term, going one back in the list of terms. How do I know I'm going one back? Because I'm subtracting 1 from the index. So I'm going one term back plus 10. Okay, so I'm adding 10 to the prior term to get the new term. So the new term is equal to, the new term is equal to the prior term plus 10, is essentially what this is saying. And they're giving me the initial. Why are they giving me the initial? Because when we write things in a recursive rule, where everything depends on the term before it, you have to give people the first term because there's nothing before that, okay? So that has to be given to you. So we can just start writing out our values, right? So when n, the index n, equals 0, because n is my index, we're using n to indicate what level of the sequence we're at, which term we're at the nth term. So when n is 0 at the 0th term, when n equals 0, they're telling me that the value at time 0, the population at time 0, is 21, okay? Now, what about when n is 1? Well, P1 is going to be, according to the rule, the prior term. What's the prior term before the first term? If I subtract 1 from this index, I get index 0. So P0 is the prior term, plus what? Plus 10. Okay, now what is the value of P0? The value of P0 was the 21, right? So I'm getting 31. Okay, what if I go to n equals 2? At time 2, the population at time 2 is the previous population. The previous population would be the population in year 1. Okay, because we're going back 1 year. Why am I going back 1 year? Because it says n minus 1. Plus, we're adding 10. Now, what was the previous year's population? The previous year's population was 31. Plus 10, so I'm getting 41. Okay, and in fact, there's my answer, because they're asking, they just want P2. Okay, but we could keep going if we want. N equals 3. P3 would be what? The previous year plus 10, which would be the 41, plus 10, which is 51, right? Now notice we're going up by 10 every year. Why are we going up by 10 every year? Why are we going up? Why is each year going up by 10? Because that's how much we're adding to the previous term, right? We keep going up by 10 because 10 is what keeps getting added. Okay, so if we wanted to, we could write this in what's called a linear equation. We could say that the population in year n is equal to what? The starting value. What's the starting value? 21 is my starting value. Also called the b, or the y-intercept in mx plus b language, plus the amount that we add all the time. How much gets added every year? The common amount, the constant amount that gets added is 10. Okay, that's the amount, that's the constant amount added every year. Constant amount added each time period, which is years in this case. Another name for that is, we can also call that the slope. Okay, whoops, I'm running out of space at the bottom. That's also called the slope, or it's also called the constant rate of change. You'll see all these descriptions of it. Okay, and now how many 10s get added? Depends on what year we're at. In year 1, we've added a single 10. To get to year 2, we had to add the initial 10 plus the next 10, 2 of them. To get to year 3, we had to add the initial plus the amount to get to year 2 plus another 10 to get to year 3. We keep adding a 10 every year, so the way to tell people that we keep adding 10s is multiply the 10 by the number of years, right? N is the number of years. Okay, notice in year 0, like P0, we'd have 21 plus 10 times 0, which means don't add 10 at all, just have a 21, which is correct. In year 1, we'd have 21 plus a single copy of 10, which gives me 31. In year 2, we'd have 21 plus 2 copies of 10, which gives me the 41, etc. Okay? So this is what would be called an explicit formula for the sequence, as opposed to a recursive rule, an explicit formula or an explicit rule. An explicit rule just tells you how to get to any particular term that you want or any particular time value that you want without having to go through the previous ones. With recursive, you have to generate all the previous ones to get to something, okay? Some recursives, it's easy to make an explicit formula out of it, such as this. Some cases it's not, okay? But in this case it is. All right, so I'm just trying to kind of, get you used to this, explicit formula notation as well. All right, so let's go to the next problem. Okay, so problem number 4 here. Again, they're giving us a rule to generate values, but notice the rule does not depend on the previous term. The rule just depends on the time value, n. Okay, that's my time value, is the n, the little subscript. And notice that's what the rule depends on. That is the main input to the rule. Okay, it's not depending on Pn minus 1. If it depended on the population at time n minus 1, then it would be recursive. It's not. It's just depending on the actual time value itself. Okay, which means that I can compute P4 directly. I don't need to generate the previous values. Okay, I could if I wanted to, but I don't have to. I can just say, hey, P4 is 55 plus 14 times the n value. The n value for P4 is 4. Okay, and I'm done. Just work that out. You get, I think, 111 in this case. Okay, so this one's really easy. Again, we don't need to generate all of the ones before this term because we're not saying Pn depends on, like if we said Pn is equal to, Pn minus 1 plus some number or something, something of this form, then that would be recursive. And then we would have to generate all the previous values to get the current one. Okay, but we don't have that here. They're giving us a formula where all we need to know is the time value that we're at currently, and that's what gets plugged in, the current time value, the current index number. We don't need the previous population. Okay, we just need to know what time value we have currently. So it's real easy. Okay, all right, cool. Okay, so in problem number 5 here, this is a recursive rule, which means I do need to generate the previous values. Okay, so let's begin generating values. When n is 0, what do I have? Now remember, what we're saying here is each term is equal to what? Each term is equal to the prior term, the previous term, plus 5. So we take the previous term, add 5 to it to get the next term. Okay, so for P0 though, there is no prior term. When we have a recursive rule, they have to give you the initial value because we don't have anything before the first term. And they're telling me the initial is 30. Okay, that's easy. Now when n is 1, we've got P1 is what? The previous value, which is P0, plus the number 5. P0 is 30, plus 5 gives me 35. Okay, and n equals 2, P2 is going to be the prior value, P1, plus 5. Now what's P1? P1 was 35. So I'm getting a 40. Right? When n is 3, P3 is the prior value plus 5. What's the prior value? 40 plus 5, I'm getting 45. Now, they want me to generate P75, so that's a lot of work. I'd have to go all the way down to n equals 75. That's going to be a lot of work, so I don't want to do that. I don't want to have to generate all those different terms, so let's see if we can figure out the pattern. Okay, and the pattern is, remember, if we always increase by the same amount all the time, it's a linear growth situation. So I'm going up by 5, and then up by 5, and then up by 5. In fact, we keep adding 5s. How do I know? Here you go. We're always adding 5s every time. Okay? That tells me my constant rate of change, or slope, is 5. My constant rate, or slope, whichever way you want to call it, is equal to 5. Okay? I'm going up by 5 every time. Okay? How many copies of 5? Okay? How many copies of 5 did I add to get to this value right here? I added 1 copy of 5. Essentially, I can think of this, if you want, you can think of this as, let's do a different color here. I can think of this as my initial value plus a single copy of 5. I can think of this as my initial value plus the 5 that got me to n equals 1 plus another 5 to get me to n equals 2. I can think of this as my initial plus a 5 to get me to n equals 1, then another 5 to get me to n equals 2, then another 5 to get me to n equals 3. Notice I have 3 copies of the 5. If you have 3 copies of the 5, that means if you're adding 5 to itself 3 times, you can write that as 5 times 3. Remember, adding something over and over again is the same as multiplication, right? This could be written as 2 copies of 5. This is 5 times 2, right? This is 5 times 1. So what's going on is we're taking the 30 and we're adding a certain number of copies of the 5. Okay, so we're doing 5 times some number of copies. How many copies? When n is 3, it's 3 copies. Right? When n is 2, it's 2 copies. When n is 1, it's 1 copy. We're adding as many copies as we have time periods. Okay, each time period we get a new copy. So that's my formula. Okay, that's my explicit formula. So Pn is this. Okay, so make sure you understand how to generate this. Don't just sort of take this result and run with it, because then you won't be able to do things on a test. Make sure you understand how we constructed this explicit formula. And once you have the explicit formula, then you can easily generate the 75th term. Just plug 75 in. Okay? In my version of this, you should get you should get 405 in this case, with using my data. Okay? And with yours, it'll be a little different. It's randomized. Okay? All right, so how do we generate that explicit formula? It's the initial plus, so that's my initial, plus, this is the constant growth amount, right? This is the amount we grow by each time period, okay? Or the slope, or the constant growth amount, or constant rate of change that we increase by each time, the amount we add each time, and this is the number of time periods, which we're indicating with n. Okay, so the amount you grow by each time period times the number of time periods, that gives you the total growth. If we add that total growth to the initial population, then we have the final population. Okay? Cool. All right, let's go to the next one.